Good morning. Today's tutorial video is going to be on acceleration. Acceleration is a word that we should have some exposure to. I think most of us, when we think of acceleration, we think, though, of this first example given, where something is accelerating because it's speeding up or its velocity is increasing. Acceleration, though, includes objects that are slowing down. It's as their velocity is decreasing, they are, you could say, negatively accelerating, or decelerating would be another word version of that. The last example we don't think of as acceleration, but when an object is moving and changes direction, it's accelerating, and we can think of it in the terms of the second B here. It's traveling in an upwards and to the right direction, but then its upwards velocity is decelerating as it starts to travel down into the right instead of up into the right. So objects that are changing directions are accelerating, maybe positively in one way and negatively in another. When we were looking at distance versus time graphs, we got some exposure to what an accelerating object looks like. Those objects are, on a graph, you start to see the distance increase quickly while the time is increasing slowly. What that means is it's traveling more of a distance in less of a time. We see an example of a graph that's decelerating. As time increases here, the object's distance is getting slowed down and not increasing. So as this line flattens out, that means distance is not increasing, time is increasing, the object has stopped. Just a reminder that acceleration can happen in both directions. This car is speeding up. It has a certain velocity. The owner presses the gas. Acceleration, the force that accelerates the car starts to speed the car up. In this case, the car is traveling in the same direction, but the brakes apply a force in the opposite direction, slowing the car down by again, applying a negative acceleration or deceleration. There's a link here where you can observe accelerating cars and some questions to answer. We have a formula that we use to calculate acceleration of an object. We take the change in velocity and divide that by the time that change takes. To find out the change in velocity, we have to take the final velocity minus the initial velocity. And then that's divided by time. You see this triangle, the triangle that we refer to as delta, but that means a change. So we have a change in velocity divided by a change in time. So we can look at an example here. A truck can accelerate from 13.9 meters per second to 27.8 meters per second in 12.8 seconds. What is the rate of acceleration? We look at these problems, we find our numbers, and we start to associate these numbers with parts of the formula. When we see a from and to, from would indicate our initial velocity. The to would indicate our final velocity. And of course, seconds would indicate our time. So we can use our formula here. Acceleration is equal to a change in velocity divided by the time it takes. What is our change in velocity? We take the final one, 27.8. That's where we're at, and we subtract from it where we came from, which is 13.9. And we divide that, meters per second, and we divide that by 12.8 seconds. 27.8 minus 13.9 divided by 12.8 is 1.0859. That's in meters per second per second. So when we see acceleration in meters per second, we see these symbols, meters per second squared. We would finally just need to go to our appropriate amount of significant digits, which appears to be 3 is the least amount of significant digits in our question. So we need to round to our third digit in our answer. So that would be 1.08 is our third digit. So because a 5 is after it, 1.09 meters per second squared. Our second example involves a car that is slowing down. You're traveling in a car that's moving at a velocity of 20 meters per second. Suddenly, a car 10 meters in front of you slams on its brakes. At that moment, you also slam on your brakes and slow to 5 meters per second. Calculate the acceleration if it took 2 seconds to slow your car down. So this question adds a little extra challenge, and something that students have trouble with is when extra numbers, when extra information are given. And so we're going to look through the numbers that we see, and we're going to pick out the one that doesn't apply to us. So we know in our formula, acceleration is equal to a change in velocity, which we can say velocity final minus velocity initial, and we divide that by a time. We divide that by a time. So we just need to find these different things. We need to find our final velocity, our initial velocity, and our time. Jetson, I am recording a video. Can you please stop? You're okay. So our final velocity is what we slowed down to. That is 5 meters per second. Our initial velocity is what we came from, and that's 20 meters per second. And what you might be seeing already is we're going to have a negative number here, and that's fine. That's being divided by our time, and if we look, we see our time here is 2 seconds. The extra bit of information that they give us that's not super relevant to using the acceleration formula is this bit here, the 10 meters in front of you. When we now apply this formula, 5 minus 20 is negative 15 meters per second. And that's divided by 2 seconds. So the rate that we slow down at, or the rate that our velocity decreases, is at a rate of negative 7.5 meters per second, which we identify as meters per second squared. The final example I'd like to do involves a question where they tell us the rate of acceleration, and we have to find out the final speed. So it's useful to write out the full formula for that one. A equals my final velocity minus my initial velocity divided by time. We have to go through the question. We have to find out what information they give us and where that goes in our formula. They tell us that the sprinter can maintain an initial acceleration of 18.5 meters per second squared. So that's our left side of our equation, 18.5 meters per second squared. Okay, the equal sign is there. We're being asked for final speed, so we don't know that. We need to find out our time and initial speed. Well, our time is given right after our acceleration here, is 0.75 seconds. The initial speed they give us, but we don't see it in a number. We're assuming that this sprinter is starting from, well, it's an initial acceleration, so they're starting from 0. So that number we'd write there, but it really is insignificant because you can't subtract 0. So we can even just erase it so it doesn't confuse us. Now we have a three-part equation. My final velocity divided by 0.75 will equal 18.5. To get rid of divide by 0.75, I need to multiply by 0.75, but I need to do it to both sides. Why do I do it to the right? Because divide by 0.75 times 0.75 cancels. And on the left side, I just need to take 18.5 times 0.75, and that gives me 13.875 as my final velocity. Velocity is in meters per second. I'm careful not to put meters per second squared because that is referring to acceleration. The last thing I need to do, I need to look to my significant digits. 18.5 is 3. 0.75, that 0 doesn't count as significant, so I just need to go to 2 digits for this question. When I look to these numbers here, these are my first 2 digits, so I have to look to that 8. That 8 rounds up. My answer is 14 meters per second for my final velocity. If you click the link, page 147 below, you'll get, I believe, 4 practice questions. They are all practice questions that you're being asked to find acceleration, so they should be relatively straightforward. The final thing I want to talk about this morning is a different type of graph. Previously, we used a distance versus time graph. We were able to look at that graph and it was able to tell us certain bits of information. A velocity or a speed versus time graph is relating the speed of an object over time. So we see in this graph here a velocity that has an upward slope. What that means is that as time increases, the velocity of the object increases. It starts from 0 and ends after 4 seconds, it's going 8 meters per second. So an upward slope is a positive acceleration. When it goes from 4 seconds to 7 seconds, velocity stays the same. So this differs from a distance time graph. What this graph shows is that the velocity is staying at a consistent rate. At 5 seconds, it's 8 meters per second. At 6 seconds, it's 8 meters per second. Same at 7. What we start to see, though, is that the velocity is decreasing as time increases, which indicates a negative or a deceleration. You have a couple of graphs to interpret for your practice. And then that will be it for today's lesson.